All right, we are in the unit 4, I believe this is packet 3. Yeah. So this is packet 3, page 1. We're going to start talking about applications of exponential functions. We're going to talk even more about growth and decay. So something that we already did is we know how to identify whether it's a growth function or a decay function. Remember, we're looking at y equals a times b to the x, all right? Most of these aren't going to have any transformations. So when we're in a times b to the x form, a is the start amount, b is the base, and x is your exponent. Remember, to tell if something is growth or decay, you look at the base. All right, so if your base is greater than 1, it's growth. If your base is greater than 0 but less than 1, it is decay. All right, so we're going to go through and we're going to identify the base on each of these and decide if it's growth or decay. On this one, our base is 4, so that means it's growth. On the second one, our base is 5/7. Since 5/7 is less than 1, this is decay. 1.4 is our base here, which tells us it's growth because 1.4 is greater than 1. The base is always the one that's attached to the exponent. All right, 0.99 is our base here. 0.99 is less than 1, so this is decay. And last one, 1.01 is greater than 1, so this is a growth function. All right. Exponential growth is when the quantity increases by a consistent percent change over time. Exponential decay is when a quantity decreases by a consistent percent change over time. Okay? So increases is going to be a keyword for growth, and decreases is going to be a keyword for decay. All right, so we're actually going to start building our own growth and decay models. This is the model that we'll use for exponential growth, and this is the model that we'll use for exponential decay. A has to be greater than 0. So y is your final amount. This is usually what we're solving for, and that's the same for both. A is the initial amount, so this is how much you start with. All right, R is either your growth rate or your decay rate. Now this rate we always express as a decimal. So, for example, if I have a 10%, if I have a rate of 10%, I need to do 10 divided by 100 to get the decimal. 0.1 would be your R. Right? Let's say I had a rate of 5%. Now to find the decimal that we would plug in for R, we need to do 5 divided by 100, which is 0.05. Right? So remember, to turn a percent into a decimal, you just divide that number by 100. That's very important. All right, our exponent most often is going to be t, which is the time. So if we're evaluating something over a 5-year period, we would plug a 5 in for t. Now, the simplified, whatever you get after you plug in your R value, this is your growth factor or your decay factor. So you're going to hear us refer to growth factor and decay factor, and you're going to hear us refer to growth rate and decay rate, all right? If we say rate, we're talking about whatever we plug in for R. So the rate is whatever gets plugged in for R. Whatever you get once you simplify 1 plus R or 1 minus R is your growth factor or decay factor. All right. Let's take a look at some examples. Identify the following equations as growth or decay. Then identify the initial amount, growth/decay factor, that's what we just talked about up here, and the growth or decay percent. All right. So the first thing we want to look at, is this growth or is this decay? Well, the first one, 1.03 is our base, which is greater than 1, so that's growth. But over here, 0.95 is less than 1, so this one's decay. The initial amount is the number out front. So for the first function, the initial amount is 3.5. And for the second function, the initial amount is 10,000. All right. Growth, in this case, we said we're looking at a growth function. The growth factor, remember, is what we see in parentheses right here. 1.03. Whereas the rate is whatever we plugged in for R. So since we know growth factor is always 1 plus R, 1 plus what would give us 1.03? Well, we must have plugged in 0.03 for R, which is 3%. Right? Now, if you want to convert a decimal, 0.03, to a percentage, you just multiply by 100. So this is our growth percent. All right, let's take a look. In this case, our decay, whoops, well, that went well. Our decay factor is 0.95. And the decay rate, let's think about this. 0.95 is what we see after 1 minus R has happened. All right, so we can work backwards to figure out what must have been plugged in for R. So, subtract 1 from both sides. Negative 0.05 equals negative R, so 0.05 is R. So since we see a growth factor of 0.95, we know that when the model was made, it was 1 minus 0.05. All right, so our decay rate is 0.05, and our decay percent is there's a 5% decay. Think about, if I only have 95% of what I started with, I lost 5%. Okay? Let's take a look at page 2. I want you to pause the video and try these two on your own, and then we will go over them when you unpause the video. All right, let's take a look. So what we see right here, our base is less than 1, so this is decay. 400 is our starting amount, and the decay factor is 0.925. So we have to figure out what the decay rate is. So we're going to work backwards. We know that what we see in the parentheses is what happens after you do 1 minus R when you are setting up your model. So we're just going to work backwards and see what did they plug in for R. Subtract a 1 from both sides, and you'll see that negative 0.075 equals negative R. So R is 0.075. And that means the decay percent is 7.5%. All right, let's look at D. Let's see how you did. This one is growth because 1.2 is greater than 1. 2,500 is the initial amount. The growth factor is our base, which is 1.2. And then that tells us, because we know that 1.2 represents 1 plus the rate. That's already happened. So the rate is 0.2. 0.2 as a percent is 20%. All right, think about 0.2 times 100 gets you 20%. All right, let's work on some word problems together. We're going to set up a model, and while you're learning how to build these models, I would always write the two models from our last notes page at the top. Y equals A times 1 plus R to the T. Okay, that is growth. Decay is Y equals A times 1 minus R to the T. All right, the original value of a painting is $1,400. So original value is our starting amount. So I'm just going to go ahead and put 1,400 in here. And the value increases by 9% each year. Well, 9%, to convert that to a decimal, I'm going to do 9 divided by 100, which gives me 0.09 for my rate. Write an exponential growth function. Now, they didn't even need to say that because they said the value is increasing. Okay, so right there with that word increase, I would know to pick the growth model. Write a growth model, then find the value of the painting in 25 years. So let's start by writing our model. I'm just going to copy down everything I see here. Y equals, we said A was 1,400, and then 1 plus 0.09 to the T. So my model is Y equals 1,400 times 1.09 to the T. All right, the reason I'm calling this a model is because I haven't plugged anything in for the exponent yet. So this could find me the value of the painting at any point in time. So I did the first part. Write an exponential growth model for the situation. Check. We did that. Once we have our model, they said find the value of the painting in 25 years. So that means we're going to plug in a 25 for T. So Y equals 1,400 times 1.09 to the 25. So that is something that we can just type straight in our calculator. So I'm going to go over here to Desmos. Got my calculator, and I'm going to type this right in. 1,400 times 1.09 to the 25. And here's what this tells me. In 25 years, that $1,400 painting is going to be worth $12,072.31. All right, so that's how much our painting's worth in 25 years if it increases 9%. All right, 9% each year. All right, the population of a town is decreasing. So which model do you think we should use? decay. At a rate of 1%